Welcome to Recording 1C in our series on Infinite Geometric Series for Unit 1, Chapter 1 of Mathematics 2200. We're going to focus our attention on converging and diverging infinite geometric series. Now, we'll look at convergence from the idea of a sequence of partial sums. Remember, a partial sum is the sum of so many terms. So, for example, S1 would be the first term of the series. S2 would be equal to the sum of the first two terms, S3 the sum of the first three terms, and so on. We can use those sums to form a sequence, S1, S2, S3, S4, etc., etc., etc. For example, if I had this series, 1 plus a half plus a fourth plus 1/8 plus 1/16, etc., on to infinity, S1 is just 1, the first term, S2 is the sum of the first two terms, which is 1 plus a half, or 3/2. S3 equals 7/4, and so on. We use those sums to come up with a sequence, which we've got right here. Notice how the numerators are nearly double each denominator. As a matter of fact, you double the denominator. For example, if I double 16, I'll get 32, and then subtract 1, I'll have the numerator. So doubling the 16 to get the next denominator would be 32. Now double the 32 to get 64, and subtract 1 would be 63. So S6 would be equal to 63 over 32. So the numerators are approximately double the denominators. And our partial sums appear to be approaching a value of 2. Let's compare that to the sum that we found using the formula in the last recording. So we check our common ratio. It's a half. It falls between -1 and 1. And so that's true. Therefore, we can apply our series formula. Term 1 over 1 minus r. That's 1 over 1 minus a half. It gives us 1 over a half. And it takes 2 halves to make 1, so our answer here is 2. So our sequence of partial sums appear to be approaching the same value as we got for the sum of the series using the formula. Graphing the partial sums provides another visual representation. So I've made a little table of values, the n values in the first row, S sub n in the second row, and plot my points, and I can see that the points are getting closer and closer to this horizontal line, S sub n equals 2, which agrees with our sum. So a convergent series is a series with an infinite number of terms in which the sequence of partial sums approaches a fixed value. The series will have a particular sum, and it must meet that condition. -1 less than the r value, less than 1, of course the r value can't be 0. Otherwise, it's divergent is the term. In other words, it will fail this test here. And the r value will be less than -1 or greater than 1. Here are 4 series we've seen before. I've already found the common ratios for each one of them. In the case of the first one, 1/2 falls between -1 and 1. That's true. And so, therefore, the series converges. It has a sum. The next one converges as well, because we have a true statement there. The third one, part C here, that's false. 2 is not between -1 and 1, so it diverges. There's no particular sum. The final one, yes, that's true. -1/3 is between -1 and 1. Now you might want to pause here and do the sequence of partial sums yourself first. So I've written out what the partial sums will look like. 1 minus 1/3 for the second partial sum is 2/3. For S sub 3, 1 minus 1/3 is already 2/3, so I just need 2/3 plus 1/9. Common denominator there, 2/3 is 6/9 plus 1/9 gives me 7/9. S sub 4 works out to be 20 over 27. S sub 5 works out to be 61 over 81. So I've done them here. It's a little harder to see the pattern from the fractional representations of the sums. So I've done the approximate decimal values. And it looks like we seem to be hanging around a value of 0.75. Let's have a look at a graphical representation. Plot the points. It looks like they seem to be hanging around that value of 0.75, 3/4. Some points a little under, some points a little over. A little under, a little over, a little under and over, etc. So we have convergence on 3/4. For this last one, I simply present the partial sums. You can confirm these. Looks like though those partial sums do not approach a fixed value. And it looks like we have divergence. We have some points that are going off in this direction, off towards infinity. Some that are going in this direction, on towards negative infinity. Therefore, there's no tendency towards a particular value, and they diverge. In summary, if an infinite geometric series converges, the sequence of partial sums will converge toward a particular value equal to the sum of the series. It must meet the condition that the r values between -1 and 1, where r is not equal to 0.